Okay, it's ready. Muy buenos días a todos. Vamos a dar inicio a nuestra serie de presentaciones de este seminario. El doctor Hendrik Hamann es investigador distinguido y Senior Manager en IBM Research. Sus investigaciones actuales se centran en la intersección de la física, el Big Data Analytics y la inteligencia artificial con aplicaciones al Internet de las Cosas y el análisis geoespacial. Sin duda va a ser muy importante y muy interesante la plática que nos va a dar el doctor Hamann, debido a los temas que nosotros manejamos en la geografía, como la gran cantidad de información que se almacena y el análisis geoespacial. Entonces, vamos a darle la palabra al doctor Hamann con su presentación. Doctor, por favor.
Good morning to everyone, and I apologize, this presentation will be in English. So first of all, let me thank the organizers for inviting me. It's my first time in Mexico, and I never realized how close it is actually to New York. This talk is about big data technologies, as it is applicable to geospatial, or I changed my title a little bit, spatial temporal data. To give you a quick outlook on what I will be talking about, a little bit about what we do in IBM. I'm from IBM Research. Quickly, why is this an exciting time for a discipline like geology, geography, etc. Talk about what are the underlying technologies, and then go through some applications where we used big data analytics on geospatial data to develop certain solutions for certain markets and industries. First, a few words about IBM Research. So IBM has around 400,000 employees. In research, we have roughly 3,000, so we are less than 1% of the population. And we are really in charge of developing the next generation technologies for the corporation, but not only for the corporation, but also for our clients. This is a list of some of our accomplishments in IBM Research. So some might remember the Jeopardy. We of course have a long history in technology, a lot of hardware technologies, computing, a lot of the fundamentals of this huge increase in computational power, which some people refer to as Moore's law, came out of IBM Research. Just a final shot on it. Important is we are not US-centric. We are, of course, a global organization. We have research labs all over the globe. We have some in Brazil, a couple in the US, but then also now we have research laboratories in Africa. So we are all around the globe. So let's go to some of the technology trends. One of the most amazing things which we witness in technology is what people refer to as the Internet of Things, right? These are, now we have sensors in pretty much everything. We have them in cars, we have them in refrigerators, etc. And if you look at that chart here, on your right side, you see that the amount of data which we generate from physical devices, that could be sensors, weather stations, etc., right, is outpacing all the other computer-generated type of data. So people usually, when they think about big data, they think about Facebook, they think about Google, right? This is all computer-generated data where they use big data analytics. Now today it is changing. It is really from data which comes from devices in the physical world. Now part of this trend, and very much in the light of this conference, is, right, there's an explosion of remote sensing data, right? So it goes all the way from something simple as cell phones, but drones, armies of satellites. We have private sectors now launching a lot of these nanocubes, etc., etc. Governments are setting up new. So the bottom line is, the bottom line is that all this data is having a profound impact on many industries. And as things develop, and I just throw up the chart for a couple of industries where you can see that in the future that these industries which have been selling perhaps very traditional pieces of hardware, that they will in the future through data from physical devices become service companies, right? So an interesting example might be automotive, right? There's a big automotive industry. In the past, they were selling cars. In the future, they will use data, including from remote sensing devices, right, to sell transportation services. There's an interesting book which talks about this explosion and what data does to everything we do to industries. It's called Dataism. It's from a New York Times reporter, Steve Lohr, and he has a very interesting chapter in that book which says big data gets physical, and it really talks about remote sensing data and how it changes the application of agriculture, for example. Now, to sort of be clear about some of the definitions, this is a plot, or this is a chart which I put together to sort of, people talk about different classes of data, right? So we have down there in the bottom of this chart, geospatial data. And you can distinguish between geospatial data, between raster and vector, and of course, and you have purely time series data. All of that is really the same type of data as you can certainly appreciate, right? And I call that geospatial, I call that spatial temporal data. Now the action and the big data applications is really in this area where we have big raster data sets, right, mostly from satellites, which really fundamentally have changed the way we have to do computation and analytics on these data sets. Now this is an interesting chart, and it is a conceptual plot, but I do believe if there's anything you want to remember from this, this is one thing you should try to think about. You can see on this plot, and again, it's a conceptual chart, but you see I've plotted here something like how easy is it to search certain data sets for different domains. And it's very easy to search the internet, right? 45 billion web pages, 0.5 seconds, and you can search it. We have made enormous progress on business transactions. We can search them. Social networks, we have indexed them, we can search them. Many different sets. Now you look at spatial temporal data, we are sort of far away from searching, let's say, 45 billion satellite scenes in 0.5 seconds, right? And that is sort of the bad news, but also the good news, right? The bad news is that we are so far away. The good news is that that is really a frontier of discovery, of digital discovery, and I think that's very exciting. This is a very simple plot which shows some of spatial temporal data sets you may be fully aware of are being generated and what is the data size. And it speaks to the previous chart to an extent that it tries to explain why it's so difficult to make all that spatial temporal data searchable, discoverable in the same way we can search, for example, the World Wide Web. And it says something about the data sizes here. This is the data rates as a function of temporal and spatial resolution of different data sets. And this is a Landsat. That's roughly 1.5 terabytes a day is being generated. Down here you have, I just put it here for comparison. This is the actual amount of Twitter data being generated. And then you have something like, just as an example, the Global European Weather Model, ECMWF, that's around 8 terabytes a day. So what does 8 terabyte a day really mean from a technology perspective? Well, if I have 8 terabytes on my hard disk, I've already downloaded that data, right? I have it. And I wanted to move that data from the hard disk drive to my memory. So So just to make that movement, so I can start to do some processing in the microprocessor, so just to move it to the memory, will take, just that data set alone will take me 22 hours. And that is big data. That is data too big to be moved. It's data, even if you have it on disk, even if you have downloaded it, it's too big. It's too big to be processed within time. And that is really one of the reasons why we are not yet in a stage where we can discover satellite data sets in a similar way we do others. Let me give you another example what is unique about spatial-temporal data. I'm wondering, does anyone know what this shows here on this picture? Any ideas? It's Manhattan. Okay, so someone really is good. It is indeed the outline of Manhattan, and these red points are these are actual cell phone locations of people using cell phones. Of course, a little bit later, cell phone people have moved. Now, that data, he knew it was Manhattan, is much more interesting if you have contextual information, right? You know where the roads are, where the buildings are, where the streets is, if you have satellite information. So contextual information is extremely important. So if I wanted to search and really do deep analytics on, let's say, satellite information, I always want contextual information. And context here means context in space and time, right? Spatial-temporal. Okay, so how do we do today most of the work? And currently, when people work with satellite data sets, what do they do, right? People in academia, but even people in industry. Well, so they're of course all experts in geospatial information processing and systems. So they know where these different data sets reside. They're in different archives. Sometimes, if it's historical data, actually the data is stored on tapes, so they have to retrieve the tapes. They have to order the data. They have to classify it. They have to resample it. They have to do a lot of steps. And fundamentally, what you do, if you do this, that's the way we have been doing business. You move the data to the application, right? Now, what we're trying to do is in IBM, and again, this is research, we're trying to change that. And that is really the notion of big data. Big data doesn't just mean it's just big. It just means you, in fact, bring the application to the data because it's so big you cannot move it. So what we do is we have created, and I'll show you some details and then some examples about this, is we have created a very large pre-processed data store of which is on a which is a global format. It has spatial and temporal joins. So Landsat is joined with Sentinel, with and with any other geospatial information you have. There's a global reference systems, and you can actually run large-scale analytics within that big data cluster, which I will show you in a second. Okay, so this is a sort of more detailed view of some of the research platforms. We call it pairs. It's just a code name at this point. But what we do here is we have subscribed to a lot of the data sets a lot of people are using, right? So these are the NOAA data sets, a lot of weather, USDA, USGS, etc., etc. At ingestion, so each time there is a new tile being a new tile being generated for Modus or for anyone, in that moment we actually grab it, we ingest it, and organize all that information in this massive big data cluster here in the middle, which is based on a Hadoop H-based platform, where all that information is being organized, where each of those in layers, where each layer is linked in space and time automatically. So none of the raw data is being stored because obviously that already is being done here in the agencies. We just create a curated, organized, aligned data store in space and time. Now the way you interact with that system is you can run APIs. because everything is aligned, you can actually run some complex queries, and I'll show that to you in a minute. And you can, of course, export this either to your favorite application once the database has done the bulk of the processing, but even more important, you can run your analytics within the data through a Spark data framework. This is a very basic chart on how do we do this alignment. This is for the space domain. We do something very similar for the temporal domain. But in the end, we have different resolution layers. Every resolution layer is nested in each other. So it's an integer of each other, which means you have a priori, once all that data is being in that cluster, it's all aligned. The Hadoop H-based system, right? That's a big data platform for people who don't know that. It uses, unlike relational databases like Postgres, etc., it is just a key value store. So you have a key, and then you have your value, which is the actual value of the satellite reading of the band, etc. So the key of that is a combination of spatial and temporal information. We have resolution layers now, and this is kind of outdated, from centimeters all the way to 360 kilometers. The length of that key determines basically what the resolution layer is, and we do this in space and time. Yeah, unfortunately, this chart is got truncated. Anyway, so here, what we have done. So I need to explain the chart. This is a very important chart, actually. What we've plotted here, and unfortunately got truncated, is performance versus data size. So you can imagine if I wanted to process something for the city of Mexico or for the whole country of Mexico or for the whole continent of the Americas, data sizes would increase, right? And so you would go up this way here, right? From here to here. And this is performance. So what the pair system does here, this is actually the performance of the pair system. It actually increases its performance the more data you process. And that is because, that's no mystery. So the bigger the query is, or the more data I want to process, or the more layers I use, the faster the system gets, or the better the performance is. And the performance, of course, is measured as megabits per second. And that is a property of a big data platform. The reason for that is because we're using more servers. It's a distributed system. So when the job is bigger, you just use more servers. All the data is distributed in a vast distributed storage system in this Hadoop H-based system. A conventional system here in blue, unfortunately got truncated again, would show constant performance. Constant performance means I process something for something larger, it would take me much more time, right? So that is really what we call scalability. Now, we're working quite hard on this. We have this ingestion engine, how to bring in the data into this big data cluster. And from there, you can interact through APIs and applications to this. But anyone can upload and contextualize its own data. We have a lot of companies and universities we're collaborating with, where they take drone images or they take some other data which they have sampled, they have some interest in. And why is that a good idea? Because once you ingest that into this big data platform, it is already contextualized with all the other information, with Landsat, with MODIS, etc. But then it is also, or with all the weather data, but then it is also can be processed within the Spark cluster. Pairs also supports multidimensional data. So most of the data I will be showing you in this presentation looks like 2D, but of course we are supporting high dimensional data, seismic data, etc. within the platform. This is the actual way a lot of people are interacting with the system. So you can actually give it a try. This comes out live at some point. And again, it is a platform free to use for everyone, helping with the dissemination and widely used type of data. Okay, so now let's talk about some of the applications. What can you now do with a platform like Pairs? And I give you a few examples. And the first example is on improved weather forecasting, right? Weather is, of course, extremely important for everything we do. There is an enormous amount of work already being done, of course, at NOAA and many other places on forecasting. Now, this is, we all know that these different weather models we have today, right? They don't agree. So this is actually sort of the different hurricane paths of Hurricane Ike. That was quite a while back. And you can see that many of these different weather models give different predictions, right? Now I have listed here, in this particular case, we actually focus on seasonable weather forecast, but I've put here some weather models which are today being used to provide these predictions. Now, when I say seasonable weather forecast models, I mean anything up to 6 months here in this particular case. And you can see these are the Americans, the Europeans have a bunch, these are the Chinese, the Japanese, they all have different models, right? It all comes at different spatial temporal resolutions. They all have different types of physics, different members, some of them are ensemble, etc., etc. So the beauty of the PAIRS platform is that all that data from NOAA, from ECMWF, is being curated. It's aligned. It's aligned pixel by pixel. So you can actually ask that interesting question, why and which model is doing better when, where, and under what weather situation. Okay? Now, to put things in perspective of some of the results I will be showing is, if you look into actually how historically weather models have been improving, that's an interesting, it comes here from a Nature paper. You can see this is a 3-day forecast, 5-day forecast, 7-10. You have two different lines, one from the northern, one from the southern hemisphere. They kind of converge. That's actually due to the fact that we're using much more remote data, so there's no bias anymore, having a lot of land versus no land, etc., etc. But you can see improvements, let's say for a 10-day forecast, over the last 30 years, we have been improving 6% per decade. And this is the actual forecasting accuracy measured by the correlation between the forecast and the actual measurements. So 6%. So the big question was, can you, if you take all that information from all these models, if you can actually learn which one of those different predictors is doing better when, where, and under what situation, perhaps you can do better, and perhaps you can change that. This is how this actually works. So we use, in our system, again, these are different layers in the PAIRS system, the forecast from Model 1, from Model 2, from Model 3. We do this actually globally. This is just showing the US. And then we go back in time and find out which one of those models is actually doing better, right? We're doing massive machine learning. We do this on the historical records of 10 years of historical forecasts. And then we use that to create a blend, to create a blended forecast based on measurements. So how do we do this actually precisely? As I said, the question really is which weather model, which prediction is doing better when, where, and under what weather situation. For that, we apply functional analysis to understand some of the errors of these weather forecast models from previous years, right? And when I say functional analysis of variance, for people who know this, right, you basically dissect the error in first order, that's a bias. Zero order, that's a bias. First order, second order, third order. First order would mean it depends on one other variable, second order on a second variable, etc. That's what you do. If you look at this here, this is actually the second order error here, this little plot. This comes from a NOAA model. It's for the location of Bonneville, Illinois. It is 30 days ahead. It's a temperature forecast. So it's kind of a remarkable result. In fact, we see that result all over the place. So if you use big data technologies and you analyze what this model has actually, how does this model actually performed over the last 10 years for this particular location, you can see that this model always underpredicted if it also predicted a lot of solar radiance and low wind speed. But hey, it was the opposite. If the wind speed was high solar irradiance, it was always over-predicting. So that's only for one location. That's only for one forecast horizon. That's only the second order error. That's only for a set of selected parameters, etc. But you can get the idea that if you start analyzing historically all this massive amount of data, fair enough, you can actually systematically understand these errors. And even if you don't find the physical cause in the models for these types of errors, you can actually start correcting this. Here's an example. I'll show you some how this works. This is a forecast for a weather station in Pennsylvania, PSU. This is the temperature forecast 30 days ahead. We see here the temperature variation, which a best model predicted 30 days ahead. Of course, 30 days later, we get the measurements, and you can see, well, you know, it was not too bad, but in certain cases, we really had something like 6-7 degrees differences, right? But that's typical. Now, we did our analysis through pairs, and in fact, these are the different weather situations which we attribute, and you can see we are not doing perfect, but definitely much better. Just leveraging all that data, which is all that historical forecast data, combining various models and then blending them together, we can create this type of result. We have extended this, only validated it currently here in the US, in the US for 7 weather stations. We do a lot in Asia. But you can see, of course, you can do this for temperature. These are this is the absolute temperature error, absolute wind error. These are the different model members of the actual NOAA models. Actually, NOAA models are one of the best subseasonal forecast models which are out there. But you can see, if you systematically analyze them, you can indeed drive down the error bar quite a bit by over 30%. Okay. Let me give you another example, which includes also some satellite observations. So now we have great weather forecast. Now can we do something about irrigation forecasting, evapotranspiration, right? And again, you're running into that issue, which you do a lot, is that to do a forecast for irrigation or for evapotranspiration, that you need a lot of information, a lot of geospatial information, right? You know, this is a simple evapotranspiration model for, you know, to understand, you know, how much water a plant loses. You need to know, of course, the solar radiation, so that's weather. You need to know wind. You need to know the soil information. You need to have an idea about the size of the canopy, the greenness of the canopy, that comes from satellite observations, etc. So I have written this just down to illustrate the fact that a lot of information is being needed. Now, today, a lot of that information is being generated, again, as we said, from different agencies at different places, etc., etc., all different resolutions. You have to be an expert to put this all together, and you will never be able to create this globally because these data sets are very big. So what we have done here, again, this just illustrates the idea, right? We have these different layers. These are forecasts, temperatures, humidities, radiance, wind. We combine that with many other layers which aren't forecasted, like the soil information, etc. We put this into this evapotranspiration model, and then eventually we create a new layer of evapotranspiration, which we can actually run down here. This is an example how this works. This is for California, validated over 130 sites for 2 years. This is the actual evapotranspiration measured in millimeter per day. This is being forecasted for, I believe, a day ahead. Yeah, it's a day ahead forecast. In green, the measurements, and then you can compare to the forecast model. This is just for California. We have actually taken this whole approach and actually are now doing this globally. So we can create readily fairly complex and sophisticated evapotranspiration forecast around the globe, which in many cases can be actually machine learned also by on-site measurements. Just to point out that all this is not just purely theoretical. We have actually also applied these irrigation forecasts to some this is actually in the area of viticulture, to vineyard management in California. And you can read some of that, you can read about some of that work also in some of the papers we published. But just doing everything remotely, using big data technologies for understanding irrigation needs of of grapes, we were able to drive down, bring up the yields 26% in agriculture, higher water use efficiency, better uniformity, and improved quality. Here's another interesting example we work quite a bit on, and that is in the area of land use recognition. This is an old area actually tried by many folks trying to use satellite information like this one, and then trying to understand perhaps there's a lot of drive, there's a lot of interest of course on in the financial industry, trying to understand who's growing what crop, for example, right? Or you can try to understand, there are many applications for that, but that's a main application, right? Trying to trying to understand who's growing what, or help farmers with certain management of their crops, etc. So what people typically do in these applications, they look into the changes of the greenness, right? The NDVI, or other forms of different satellite bands. So for example, you see here as a function of time of the day, the change in NDVI in the greenness from the Landsat satellite. And theoretically what you would see is, for example, for soybean versus corn, which is very popular in the Midwest, right, of the United States, you see that corn gets much faster green than soybean, etc., right? And then you use that information to decipher, okay, who's growing soybean, who's growing corn. Now you can imagine if you only have corn and soybean, that might work okay. If you have many other crops, or you look into other more complex applications of land use, this will get much more complicated. Now in pairs in this big data platform, we have, of course, a big advantage here in many cases, right? So for example, we know the way these curves look like, they will definitely depend on weather. We already have contextualized weather information, right? We know the way these curves will look like will definitely depend on soil, on the soil type, right? It will depend on temperature anomalies. It depends on snow melt, on all kinds of issues. Now, having all that contextual information, and also having that information previously in the US that's actually published later on who's growing what, you can do a massive machine learning exercise, not only using satellite information, which is of course a great source of information, but has also of course a lot of issues with noise, but a lot of the contextual information. That's what we do quite a bit. This is an example of some of the crop forecasts which we do in pairs. These are all areas for different crops. The different colors indicate actually different crops. This is actually somewhere, I believe, in Idaho. So there's a farmer here, we've done it all the way to 2005, a farmer who actually switched back and forth between potatoes. And this is actually down here, winter wheat. And so he switched back, and you can actually then also understand from the rotation pattern, you know, what were the choices here, right, for this. So that's an example. So let me get you another example. This is sort of still exploratory work, what we're doing with the pairs technology. But one interesting aspect, of course, of all the satellite observation is, of all remote observations, or in general even, that you have this disconnect, right, between you either have high spatial resolution, but then you don't have that observation that frequent, or on the other side, you have low spatial resolution, but very frequently, right? That's a fundamental issue which we all have, right? I've plotted here, just for the fun of it, the spatial resolution of different satellites as a function of the revisit rate, which is, of course, then the temporal resolution, right? You can see here our ghost satellites, right? For obvious reasons, right? They have poor spatial resolution, but they come by very often. But then on the other side, you have very high resolution images, some of the commercial satellites, which maybe see something at a few centimeters, etc., etc. But you can see it nicely lines up, right? So you have this disconnect between this. And we're doing some interesting work where we are trying to see whether we can really use concurrent observations from the last 10 years where we had at the same time an observation, let's say almost at the same time, an observation from a modest satellite, of course at many different spectral bands, and the Landsat satellite. And can we then learn the deconvolution function between, or the actual transfer function between that, between these different satellite observations, right? So here's an example. This is actually the Tappan Zee Bridge. This actually happens very close to where I live, and you can see here down in this high resolution satellite image, this is the existing bridge, and then they built a new bridge right next to it, and these are actual building pillars you see here. A lower resolution satellite at the same time sees this like this, right? Everything is a little bit smeared out. Of course, the contrast is different, etc. Using a lot of contextual information, but mostly these two images. So can I then, if I have enough of those, if I have that for the last, let's say 5-10 years, so if I have thousands and thousands of that, can I actually learn that transfer function? And we have done some experiments. This is an experiment of a high resolution observation which we got in, this is actually in Silicon Valley, and I just want you to focus on this red circle. High resolution satellite comes by a couple of, actually a year later, and you can see if you just look at the red circle, right, there was a major reconstruction in this area here. So how does it look in a low resolution satellite? You can see that, just look at the red circle. Yeah, you see something in there, right? But it's barely recognizable, right? Now we went back for this and started training these images on when we had concurrent observations. And you can see this is actually the deconvolved images. And you can clearly see, now look at the red circle, you can clearly see the resolution enhancement. So what I'm trying to say is having the contextual information from multiple satellite information opens up a whole bunch of unique opportunities. Here's another interesting example we do in pairs, and I think after that probably my time is up. But it is on industrial productivity monitoring, right? So it's I'm obviously working for a commercial entity, so there's a lot of interest from people to understand what is the productivity of certain facilities around the globe. In this case, we're talking about aluminum smelters, right? Aluminum smelters, you can imagine, they pump out a lot of heat. So what we do here is, and you can see that we go all the way from the bottom. The bottom has all the pairs information, but we create a model which basically looks at the emitted heat content, right? And for that you need, of course, weather information, you need wind, because a lot of the heat convection is done then eventually by weather information. You take the satellite information and put this all into a heat output model, and then you use that to see whether you can actually see that. This is an example where we actually looked at an aluminum smelter in China. And you can clearly see, we had some validation data. You can clearly see this was the actual, you can see here, this is the predicted and this is the actual measurement. And you can see here right in the middle, we are actually doing a fairly decent job to monitor this for this aluminum smelter. Let me give you, well, another example just to summarize this. This is around using feature recognition with deep learning. We're actually working here with high-resolution LiDAR data. In this case, a high-resolution LiDAR data, which was actually taken not too far away from here, over the Mexican jungle, and was very complex data, and was done actually for folks who wanted to learn about whether there are pyramids under the jungle. And so what we did here was we used multiple sources of information, trying to see whether there are areas of ancient structures in the jungle. And you can see actually this is a temple, which we were able to recognize out of this LiDAR mess. In fact, we used deep learning, and we used satellite information plus the LiDAR data, because what you can see, the greenness of the trees under structures, right, which are buried under the trees, is actually affecting the vegetation. And you can see this is actually temple. There are different houses here, etc. These are walls, etc., which was deciphered from this satellite set. Okay, and with that, I want to conclude and hope I have some questions. Thank you.
Muchas gracias al doctor Hamann por su presentación, ha sido muy interesante. A nosotros en particular nos interesa mucho la parte del manejo de datos. Actualmente en el Laboratorio Nacional de Observación de la Tierra recibimos 2 terabytes al día de información. Entonces es un problema que tenemos que manejar. Pasamos a la sesión de preguntas, por favor. El doctor Aguirre y después, gracias.
Good morning. It was a very nice presentation. It just clarified to me many things. No? But I was just wondering about the noise. I mean, you were talking about the convolution of the images, and you were using high-pass filter. But I mean, I think the noise will be increased using different kind of data. And if you applied, a powerful high-pass filter, the noise will be increased. Another thing is, I think you have to multiply the entropy of the data, or I don't know, many factors. Also, the chaos theory, includes some of the noise in the data. How to deal with that?
Yeah, so I think you ask a very good question. So on a high level, it is a good question for the main reason, right? The whole promises of all the work we're doing, right, in the IoT space, right, where people predict trillions of dollars, right, will depend on, can we deal with noise, right, from these sensing systems? Same thing for remote sensing systems. How do we deal with noise? And I think it's a tough problem. It's a very tough problem. And the only way I do believe we can deal with noise is in the same way we can deal with security, right? Security is a tough problem. And how do you deal with security? Security is always you have an independent system in place which is not affected by the first security. So you have different layers. I do believe there is no way we can get around this, is that we have independent sets of information. And we learn how to fuse these independent sets of information to drive down the noise. So in the examples I showed is right where the deconvolution is of course a classical case, right, where you are prone to very tiny amounts of noise. Now, if you couple that with with any model, it doesn't have to be machine learned, right? But with any model which is a descriptor of that noise, which might be really moisture content during the observation, weather data, which might have other things, right? The more you know about this, the higher degree, and the more data, of course. It's not just the more you know. You need a lot of more data to be confident. You can drive down that noise, and that's the only hope we have. And this is a lot what we have done. So how were we able, for example, to overcome the noise issue in the crop recognition or in the land use recognition? Because that work has been done. People have tried it to use satellite information to figure out, and they are doing it today. The key I believe the key there was, or what we learned at least was, hey, if you have perhaps information from other satellites independent, that's one, but if you also know a lot about the soil, if you know, et cetera, right, that drives down the noise, and the only hope I can see we can overcome that. But a very good question. Thank you.
Doctor Magaña, por favor.
Hi. It's related to the 30 days forecast, weather forecast that you presented. And I have a problem with that because there is supposed to be a theoretical limit in terms of how long you can predict deterministically, which is about 2 weeks. Now you're trying to go 30 days for the weather forecast. And we all know that ensemble forecasts are usually better than individual model forecast. So what we saw in your presentation was that the ensemble was better. I mean, I suppose it's a sort of average of the various models that you convert into an ensemble forecast, the blue bar that you presented. Now, the question is, if we agree that there is a theoretical limit to the range or to the kind of forecast you can prepare, how are we going to deal with the uncertainty after those 2 weeks limit? Are you working in dealing with the uncertainty? Is it just a matter of higher spatial or temporal resolution in the models? It is not, obviously, but how are we going to really deal with that in terms of making useful forecast at that time range?
Yeah, so maybe three parts to this is, of course, what we presented is not an ensemble, right? It is an systematic learning about the strengths and weaknesses of different forecast systems as we were able to observe them for the last 10 years. And I don't think that had been done in the past as systematically, especially not with that many models, and that created a better forecast. Now, the whole notion of uncertainty, so first of all, if I'm a physicist by training, if someone talks to me about uncertainty, the first thing I think about is Heisenberg's uncertainty principle. Obviously, that's not what you're talking about, right? But that is what's fundamentally uncertain to me. Right? Yes, there's nothing I can do. That's a law of physics. I think what you're referring to is uncertainty in all the observations we have to validate, et cetera, right? And if you add this all up, we have not addressed that, and that's a very good question as well, right? So what, given the uncertainty of all the observations, how far could we get with this, right? And the one thing is, though, I want to say, is when you do this machine learning, right, this multimodal blending, of course, the beauty of these machine learning techniques is the uncertainty within the training range. And you can argue whether that training range of 10 years is sufficient or not, and may not, right? But you at least know what the uncertainty is given that training range, right? Because that falls right out of the machine learning technique. Okay, but maybe we can discuss later. It's a very good question.
La siguiente pregunta, por favor, adelante.
Thank you. Thank you very much for your presentation also. And then thank you for the excellent choice that you made with those 6 examples. The question is, nowadays the crowded source is a very, very important source, especially here in Mexico at these times. Have you dealt with that? Can you mention some example of that?
Yeah, so yes, we have actually. So we do a lot of work on sort of people who are interested in either supply chain or marketing or shipping of goods. So the pair system is actually a great system because we have feeds of geocoded social data. And that's typically, so we can then easily run a query into that system and say, hey, where in Mexico people are twittering about whatever, the new iPhone, right? And tomorrow it's gonna rain, so they might be likely to go to the mall, right? Something like this. That's a very typical situation which we have, right? Yeah, we worked with social data quite a bit, geocoded social data quite a bit. All the examples I showed, yes, they were heavily on the environmental sciences side. To me, from a fundamental technology perspective, hey, that all applies to health, to economic data, pricing data, right? We know that I showed you the commodity, the crop recognition data, right? So of course that data is interesting in respect to the pricing in different places around the globe for corn, for commodities, etc. Right? Yeah, but good question. Thanks. Yeah, we have dealt with it.
Thank you, Dr. Hammond. Thank you for this interesting talk. I have a different kind of question going more on the technology side. I mean, you basically talked about a race between data generation and technology. I mean, I was really impressed about the amount of data that is generated by these weather forecasting systems and all that. I mean, and you basically said that it's unthinkable to just try to move them from one place to another. So my question has to do with what's the future of technology in the sense of being in an environment where we will have more data being generated. I mean, you said that the Internet of Things is going to generate as much data as other kinds of computer-generated things. So does that mean that we'll have to change the paradigm in terms of the way we think about technology right now?
Yeah, so thanks. Another good question. Yeah, so let's take weather, right? Just to put that in everyone's, just want to reiterate that point, and then I try to answer that is, so people realize this. So roughly a petabyte of weather data is being generated every day. So what is a petabyte? A petabyte are 10,000 servers. 10,000 hard disk drives, high-end hard disk drives. If I wanted to process this in a day, I would need 1,000 high-end servers, right? If I wanted to do this in 1 hour, you know, I would need 24 times that much, which means it's a full data center. It's a data center the size of this building, right? So petabyte a day, a data center a day, that doesn't add up, right? So that is, I think that will be a big challenge, right? How to deal with that. So of course, technology. So what on the technology side, what has happened? Of course, we have been improving technology quite a bit. So while the data size have been exploding, right? We have gotten much better in processing that data. How that will be in the future is a very good question. Of course, we have now technology like cloud computing, etc. But I think there will be much more emphasis in the future on really leveraging all that data which we've already collected. I go to so many meetings where people say, oh, we want more measurements, we want this, right? And we haven't even looked. Landsat we have looked at that, this is the tip of an iceberg we've looked at. And I think I'm not the only one who's saying that. I've heard other people saying that. And so it will really come to us to see, you know, how can we actually collaborate? It's a matter of collaboration, because one thing is true too on the technology side is a lot of these things are now still in silos, right? And so can that be consolidated? Can we all work on the same data sets, right? Can we really use cloud computing for this rather than moving that data, right? You have your cluster, next university has their cluster, every university, every professor in the United States who gets a grant, right, wants to buy a couple of new machines to have his own data set. So I think these will be the sort of the trends we see. On the technology side, I can see, of course, I can just say there's constant improvements. Whether we're going to be able to keep up with that, probably not, right?
We have time for one more question.
You talked about discoverability and searchability. How exactly this pair system is providing tools to move towards a direction in which this geospatial information is queryable and searchable?
Yes, yeah, I wasn't too specific about that, right? But show me all areas in Mexico, for example, right, where the satellite information says XYZ, the weather gonna be, the weather was 10 years ago bad, something like this, such a query, such a search. That is a single API call with the pair system, right? The pair system will be, as I said, we make an IBM, we make a larger announcement later, and it's actually free to use for everyone, non-commercial. But this is what I meant. So basic queries, which we have, you know, how for example, when I talk about this, a lot of people sometimes are a little bit confused. But how, for example, in the banking industry, where you have a lot of transactions, which are super fast, right? What was a big breakthrough there to do all this that fast? And it was really a databases. There's a big difference between a bunch of files and a database. A database does a lot of query work for you, right? You query these things you want from all these different dimensions of your data. And that's exactly what the pair system does, right? So it allows you to search, run these queries into the system. The results from the queries, as I said, can be exported to a Spark data frame within the same cluster. Again, you're not moving the data. You can actually then run your Python codes within the Spark cluster, and the data was never moved really fundamentally from where it was stored, or just a tiny bit.
You have a question? Okay. Thank you very much, Dr. Hammond, for your interesting presentation. Thank you very much.
Gracias.
Thank you, Dr. Hammond. Bueno, ahora iremos a un receso para volver a las 11:30 al panel 1 de aspectos sociourbanos y territoriales. Quienes gusten pueden pasar a visitar la biblioteca del instituto, donde hay material del INEGI para su consulta que se ha puesto a disposición. Muchas gracias.